We started out, my wife and I, we have 4 children now, 11 grandchildren. We started out with public school, private school, and our last 2 ended up homeschool. So we've been through the gamut. I understand almost all those different scenarios, and I've been pushing homeschool ever since. So daughters did fine. One graduated from Auburn University in marketing and has a matter of fact, when she graduated, she was making more money than I did. But we also, with homeschool, believe that learning something in the field that you were studying gave you an advantage over the other students who were just going to school to get a degree, because now you have experience and a degree, and it's worked every time with all of our kids. They got really good jobs coming out. My oldest son, who didn't even want to finish school, who was really smart, got bored with school. We didn't even consider homeschooling, unfortunately. Basically ended up later on and got his master's degree. He was skipping school. That's how bored he was in school. So I really appreciate all the effort that goes into it, because I understand it. We've been there, done that. And on that note about homeschool, we have some new friends that feel like we've known them all our lives. Jordan and Marie Foote, their 2 children, Micah and Megan, they homeschool. They live in Costa Rica. They're missionaries. And I met them last September. I went on a mission trip with my wife to help take care of another family, and they live up the street, and we met them, and we had lots of things in common. Entrepreneurs, I had a few businesses, so that was in common. Coffee was the big one. And we've actually started a coffee company, and it's Santa Maria Coffee, and so we sell that coffee to help people go on mission trips and help pay for missionaries. And the really cool part is they're helping people go into Muslim countries which are closed to Americans by sending Costa Ricans that are Christians and sell coffee. Duh, it's obvious. It's their deal. So that's them. They're here, and we've been talking the coffee bag project ever since we met them, because I've been doing this for 2 years, and they, of course, were in it. So that's what they really wanted to see, and they homeschool them to see how we do things, or you do things, and I appreciate that we're intruding. And then Christian is another friend of mine, and the project, the materials and things I'm going to talk about is the shuttle program. That's why I worked 10 years of my career on the space shuttle program, external tank, specifically. Christian and his brother are homeschooled also. Christian's dad worked on the shuttle program from the time it started to it ended, which was 30 years. He wrote a book, and now he's traveling around the country doing book signings, and he's just so talented. Well, his son, I found out, was doing his website and some really cool videography and photography, so I asked him to be my photographer, of course. And he's homeschooled, and it fits with everything we're doing. So that's all we're doing here. So without any more ado, we can get started, because we have a limited amount of time. This is a program that I kind of cut my teeth on. I started at NASA on the shuttle program in 1984. I worked on it until 1994. I spent 10 years of my career. When I first went there, I didn't have my degree. I was a technician, but I liked what I was doing and excelled. And I ended up with 3 patents while I was there on materials and processes that actually made the things I'm going to show you later become flight hardware. So materials just seemed to be the thing that I understood. I didn't have any training, I just understood it. So it's like, as I watch kids, I love it, is you discover who they are, because they are who they are. It's hard to make them into something else. But if you discover who they are and help them with that, they can be very successful and will feel very comfortable in their skin. So that's why I like doing this and being with you. So we're going to find out through this process, I believe, that some people just are automatically engineers or scientists. I have a granddaughter out of my 11 grandchildren who's just from 3rd grade on. Kaylee knows her, Emma. I bring her to work, and she'd be down with a lab coat hanging down to here, and she'd be sitting there making stuff. And now she's on an engineering track. She loves this stuff, and she's kind of my main spokesman for the Sunshield project. So, the external tank. You all heard about the shuttle? How many heard about the shuttle? We no longer do flights on the shuttle program. You understand that? It's no longer happening. This is the shuttle. These are the solid rocket motors, these white things on the side. If you look at it over here, that's the solid rocket booster. There's one on the other side where Glycol built those. This is the external tank, which was hydrogen and oxygen in those big tanks. And they're all orange because they had a foam that was sprayed on it. That's materials. They had a very lightweight foam, less than 2 pounds density, which would be very similar to styrofoam in packing. If you open up a box and had that white stuff that's in there,
We call it ghost poop.
a little things, yeah, that foam stuff. Well, this is designed specifically to go in space. This foam, it's not just like everyday foam. It's a urethane foam that allows it to ablate. It kind of comes off real small little pieces as it's going through the hot atmosphere. So that was the project I worked on, was the external tank, and the people that I worked with were developing a new foam. The original foam was designed with HCFCs. Y'all maybe heard of hydrofluorocarbons, the things that are depleting the ozone, so we had to get rid of them. So they went to CFCs, which was a perturbation with less HCFCs. Well, then what I did is I was trying to come up with something that was going to solve the whole problem and not have CFCs in it at all, which I did, and that was one of my patents, and we'll talk about that in a minute. But if you look at the structure, you got a clicker or a thing on the bottom, or what am I doing now? Okay, materials. What are materials? Lots of hands. Yes, sir.
Inanimate objects that you can use to build, project.
Okay, Bill. So do you have any materials right there near you? There's one. Okay, young lady right here. What else?
Materials can be, they're objects that can make up the world around us.
Everywhere we look, we see materials, don't we?
And face covers.
Materials. It's all around us, right? Go ahead. Yes, Mike.
The materials is something you can use to build or create. It's at it could be either at an atomic level or at a huge level. There are things that make up the world around us.
Right. Very good. Okay.
Mr. John, the face time.
Please time quit. I expect.
Just
Okay, I'm ignoring it now. What do I do?
You have to tell it that you're ignoring it.
How do I
it's
tell it?
twisted world.
I'm ignoring it. I'm not a computer.
You're very funny, John. Mr. John.
Oh, he ignored everything. Okay. Very good. I'm glad you. Thank you. There's always somebody, you know. It takes all kinds of people. Kaylee, that's what I love about this project. We're finding out, and why I like working with students are, some people are just really good at some things and some are not. Computers are not my thing. I hate them, but I have to use them, and they're just what they are. So, why are they important? Yes.
They make up everything in the universe, including you and everything that we eat and drink and everything.
Yes. I mean, that's kind of summed it up. I'll let that be the answer. That's why I like it. Everywhere I look, there's materials, and what I was thinking is how to take materials and create other things that are not normally made out of those things. That's where the creative idea comes in, to make it. We're going to go on to the next question. So how do you choose the right ones? Yes, sir.
The ones that are the best suited for the job. So if you wanted a drill, you would choose the most sturdiest one. Like you would choose an iron drill instead of a copper drill.
Maybe. It depends on what you're trying to drill into. So if I was trying to drill through concrete, I'd use a masonry bit, a masonry drill. It's designed specifically with a certain kind of hardened tip on it to be able to go through concrete. If I'm going through plastic, would I use a mason bit? Not necessarily. I might be able to get a hole. It's not going to look very good, but we'd use a certain kind. Yes, right here.
What's the mason drill first?
It's a certain kind of bit, a drill. We call it. It's a thing that goes in, a drill motor, a power drill. The thing that goes in and makes the holes. That thing is called a mason bit. And the reason it's called a mason bit is it's made for masonry, which is concrete or concrete block or stones or something like that. It's a very, very hard tip on it, so it can get to the rock. Because if I use just a hardened steel tip, I'm not going to get any hole. I'm not going to make a hole in the rock. It's just going to end up with a dull drill. Yes, sir.
And the way to choose the right materials for something is to experiment.
Okay, experiments are a good thing, but in the beginning we have something we're going to make or something we have to accomplish, right? So I'm going to bring it into what I think we're interested in here, and that's rockets, right? We're talking about rockets, so that's what I'm going to show you is rocket stuff. Because that's what we're interested in this particular class, right?
Right.
Look, this must be the other one. Okay, this one. Okay, so if you go back to that picture of the external tank, this big thing, and then there's, if you stood it up, and then there's a top of it, and has a big spike on the top of it, that's called the nose cone. That's the very uppermost part of the shell program. On the sides, though, there's two. Remember I told you there was two kinds of gases in the big orange thing? You know, liquid hydrogen, liquid oxygen. Well, in order for those to get mixed, you have to have lines from the oxygen and the hydrogen so they mix together to create the thrust at the bottom. You know, this is our fuel, liquid fuel. We had solid rocket fuel, which is like the rockets you all have made, and we had liquid fuel, which is in the big tank. Okay? So, this particular part here is about this big. And it's shaped kind of like a hood scoop. You know, a hood scoop on, maybe on a race car, you see a hood scoop out on the front, ram air blows into it.
Or a shovel.
Pardon?
Or a shovel.
Well, not quite. But it
If
has
you
a
turn
shape
it
similar
upside
to it. Huh? But this is done this way. This sits, so the tank is here, the tank is big and round right here. This is sitting on the tank. And what happens is, this is the hydrogen fairing. The gaseous hydrogen line comes out of the tank up here like this and down along the side of the external tank. This then is on the upside going through space, so this has an aerodynamic surface on it. You all talk about aerodynamics, right? So when the wind hits it, it doesn't go bam and slow things down. It just flows over it very smoothly. So this is what it was made out of originally. It was made out of a formed aluminum, a special aluminum, metal aluminum, and then they sprayed it with that orange stuff. What was the orange stuff again?
Oh.
Foam. Very good. Yes, foam. So this became the ablative that kept the heat away from the gas, the hydrogen in there, because we don't want the hydrogen to get hot, it will explode. Right? We want the hydrogen, that area to stay cold. So the task, this is the first one I started on 1984, was to be able to take this part, which had all kinds of rivets and all kinds of parts and welding and stuff to make it become this one piece. We replaced it with this one piece made out of graphite, carbon, and epoxy resin. So this is all one molded piece that eliminated all kinds of parts and welding. This did not have to have any orange stuff on it. So now it's lighter, stronger, less parts, and still accomplishes the same goal. It's aerodynamic, it keeps the heat away from the gaseous hydrogen. Does that make sense? Whitney, is that?
Yeah, I was wondering which elements made the heat made it not get hot in the nose cone?
In the nose cone? We'll explain that in a minute, okay? The foam acts as an insulator. Why do we put foam into boxes and in refrigerators and things? It's to help keep stuff.
Yes. To keep stuff from getting damaged.
Foam, yeah, foam in packaging is used to keep things from being damaged. If it's hot and cold thing, we can keep things hot or we can keep things cold, right? So foam is that. So this kind of foam was an insulating foam, but it also acts as the heat would go on it, the foam would dissipate, take the heat with it. That's like when we sweat, the sweat takes the heat from our body and allows us to be cool. That's what sweating helps do. This is what materials does for this particular part right here. Does that make sense? You follow me? So we took this complicated part here, even though as small as it was, and we reduced its weight by over 50%. Why is the reduction of weight important when it comes to rockets and thrust?
Because you need less thrust to get it in the air. If it's too heavy, you need more thrust, which makes it even heavier.
Right. Whitney, what else? What is that?
Because, like, with our water rockets, if we use like 75% of one of these giant Coke bottles of party sizes, 2 liters, it could, it could shoot the water bottle up, but it could shoot the water bottle up or something, but it can't shoot up like a cannonball or something.
So if we actually took your bottle rocket, right, as you normally shoot it up, but then we added something on top. We put a little nose cone on top of it and put a little ball that weighs like 3 ounces inside it, just a rubber ball. We want to send a rubber ball up into the atmosphere with the same amount of thrust. Would it go as high as it did? That's the right answer. Very good. Okay, so let's move on. Enough of that. Just so you know what's going on. Okay, so now we're going to go.
Also, more weight can also mean more drag, which could stop it from getting into the atmosphere.
Right, and why is that important? Because we we have a goal, right? We want to get so far, right? Don't we have a mission? We'll call it a mission. We have a mission with the JWST Space Telescope. It has to get 1 million miles into space. Well, it isn't going to get there unless we get it out of the atmosphere and on its journey at a certain velocity, which you talked about figuring out, or else it's not going to get there. All that is related to weight. So Mr. Jason he keeps up with the weight of everything that goes onto the James Webb Space Telescope Sunshield. And it's thousands of little things. It may be something, I'll give you an example. It may, and there's a lot of these things. There's hundreds of little washers about this size, but they're not this thick. This is really thick. This is 125 thousandths thick. These are 1 thousandths to 5 thousandths thick, which is the thickness of about the thickness of a piece of paper. But there's thousands of them. If you take 1,000 of those things and stack them up, does that weigh something?
Yeah.
Right. Does it weigh more than one thing?
Yeah.
1,000 times as much as one thing, right? So if you put 1,000 of these things and 1,000 of those things and 1,000 of these and 500 of those and 7 of these and 20 of those, you got to add all that up. It all becomes part of the weight, the mass that we have to deal with in the program to get it up in space. So back to what I did in those 10 years, we had 5 parts that were candidates for less parts and lighter weight to help the shuttle now take more science and experiments up into space with the same amount of thrust, the same solid rocket motors and the same oxygen tanks. Does that make sense? So if we can take weight off of the structure, the rocket engine, the nose cone, and all of those things, that gives, and with a certain thrust that we're stuck with. But if we can get that down, now the rocket can go higher, right? Get there faster, or we can put payload. And payload is important because of the word pay. People who pay to load that stuff on there to go into space. So commercial space is only going to work if we can get it cost effective enough so that someone will pay for putting a satellite on it to send it in space. Does that make sense? So materials, I love it. You got to figure out a way to make things as light as possible, but still work.
By experimenting.
And that's what I do all the time. That's why I love my job. Every day is a new day, right, Jason? It's like we're doing experiments right now. I mean, even though I'm not there, the guys in the laboratory are experimenting right now. Yes, sir.
Does fiberglass go into space very well?
Fiberglass has gone into space, but it doesn't go in as well as some other glasses, which is this one I'm going to talk about right here. Okay, what we have is so this one, see how big this one is? This thing right here? That is like, see, remember the little one? This is the one, this is a big one. This one was this tall and about that long. This is the liquid oxygen fairing, the LO2 fairing. So when we did the little one, they go, hey, can you do big things? So we made this big one. Look how light it is. I'm holding that up with one hand. That part was made out of aluminum and rivets and welds and all that foam stuff on there. I could barely pick it up. This is one. I'm picking it up easily with one hand. So now that took us several more pounds off that could go into payload. After we did that one, they did this one. This was the inner tank access door. So if you look at the shuttle again, the external tank, in the middle of it, you see these like ribs all around. It's called the inner tank. That connected the oxygen tank and the hydrogen tanks together. It's called the inner tank section. They needed a door. This is called the inner tank access door. This was made out of composites, but what we needed to do to make it strong, we couldn't just take something like this, flat, and be strong enough, because there was no strength in it. You know, it would just be this floppy kind of thing, even though it had a shape like that. So we put what are called rib stiffeners in there. But the thing was, the material that they had given me to do the rib stiffeners could not withstand the temperature of the cure of the composite material and the pressure of the autoclave. So we put it in there and put pressure and vacuum on it. The foam ribs they gave me crushed. So this was the inspiration for me to come up. I designed, that's my patent. I developed my own foam that I could use in a structure at a certain temperature and pressure in order to make these ribs actually survive the process and then become a real part in flight. Does that make sense? So they had a goal. We want to make this tank door lighter, but it has to have certain structural strength. So you have to design those things. Jason would go, okay, here's my material choices. I've got to design it. Maybe if I put ribs in it or stiffeners in it, I can make it thinner but still stronger. That's how we come up with it. Then we would go and experiment with that stuff to see how it turned out. This is the crowning joy of the whole thing. So finally they go, this is the thing that sits on the top. This is the topmost everything of the shuttle program. I mean, this is the lightning rod on top of the external tank. This part fits right on top of that big hydrogen orange thing. This thing, I got a patent on this process, figuring out how to make this also. This is all made by hand. Every one of these things is made by hand. This became flight hardware, 100% successful missions. Not a single one failed. But we used composites again. Less parts, lighter, stronger, and it didn't have to have the orange stuff on it. So that's material. Is that cool? How do you get materials for rockets? Yes.
I have a question. How many, I'm sure you did, how many tries to create that patented ribbing thing that you created? How many unsuccessful tries did you have before you found the one that was actually going to work?
That's very interesting.
And how much time? I'm curious.
It was probably over a 5-year period, because that was not my job, right, Jason? That was something I did on the side, because I had other things to do. So in my spare time, my brain's figuring out how to do this. So the foam development lab was next to me. I worked with a PhD in chemistry over there and said, hey, I got some ideas. And so he gave me some chemicals, and I fooled around with it. So whenever I was doing oven cures, I would check my stuff in the oven until I finally did it. But it took about 5 years to figure out the right one.
And lots breaking over those 5 years.
Pardon?
Lots of them broke over those 5 years?
Yeah, smooth. The biggest problem was they would crush under autoclave, over 350 degrees Fahrenheit, 100 psi, and full vacuum. They would just. I wish I had some pictures, but I didn't want to get too complicated. But if I showed the thing goes like, it has the composite on the top and the bottom, and then it go. It just crushed down in the middle.
So
yeah.
kids, if he'd given up at 4 years and 11 months, roughly, would he have discovered the one that would work?
No.
Nope.
So this goes along. Who's ever heard of Thomas Edison?
Ah, we just talked about that.
Okay, so what was the interesting thing about Edison versus Einstein in their thinking about stuff? Einstein's like I am. I mean, not like I am. He was in his head thinking things, math things, figuring out, this way. Edison would take things, and the one he's famous for, and I forget exactly what the numbers are, but how he was interested in inventing the filament for the light bulb. Do you remember that story? He tried hundreds of different materials. He was getting materials from all around the world to figure that out. Yes?
Well, he kind of did it outside of his head, Edison, that is. And another question, did anything explode while you were messing around with chemicals?
Yes, I did. So I had some small explosions, yes. Fortunately, I'm still here and they weren't that bad. But I had one explosion with a foam where I was working with a chemistry student at the university. And I'll show you, well, I didn't put that part in here. We were building a tool for a liquid oxygen line. It was 5 feet long, 9 inches in diameter. It looked like a big L. And we were pouring 5 pounds of the foam inside of there. And when she mixed it up, do decimal points matter? I mean, it's back in math. Does it matter where the decimal point goes?
Yes.
Yeah, okay, so if I'm going to pay you $100 an hour, and we agreed on $100 an hour, right? So and no cents. How would I write that? I'd write 1, 0, 0.00, correct?
No.
That's dollars and cents. Yes. Yes. 1, 0, 0.00. That's $100. Okay? Now, it's time for you to get paid. And I accidentally moved the decimal point that way. So now I get 10.000. Would you be upset?
Yeah. Oh, yeah.
Why?
This is $10.
But it's just a decimal point, it's just a little period. Yeah, that's right. It matters, doesn't it?
Especially.
That's right.
It's a joke. Because
Yeah.
there would be
Yeah.
too many cents.
We don't have it's too many cents. It makes no sense. It's nonsense, right? Okay. Very good. I love it. Okay. So, sample, we're going to talk about some different things. I brought some samples with me. Okay. Now, all of these are cylinders, and I want you to keep this one in the back. Okay, because I want you to just kind of hold it. Okay, I have a wood rod. Let's say we need a rod for something, so I have wood. Could be the rod. I could use a steel tube, right? Looks very similar, right? Or, in this case, I brought, and there's many more choices, but I'm trying to keep this simple. I brought a graphite rod.
Why does that one have to be in a bag?
Because you'll get black. It's graphite. I don't want you to get it on.
Oh,
okay?
It's what's in the picture.
Well, it's carbon and not graphite. No, aluminum is aluminum, graphite is graphite. But this is carbon. It's like when you burn a tree log, that black stuff that's left over, that's carbon. That wood is turned into carbon. This is carbon in a special form that we use that I formed because I was going to do something on it because I needed it to act a certain way. Okay, so I'm going to explain what I was going to do there, why I have the three different ones. What I wanted to do was, I wanted to spray metal onto this, but then take this out of the inside of it. I've done this. I could spray metal on this wood, but then I have a very hard, I got to drill the wood out, right? Because I can't, there's not a chemical I can put on it to make the wood go away and just leave the metal shell that I put on it, correct? Does that make sense? I can't, it's hard to get rid of this on the inside, it'll be kind of stuck in there. Now there may be an application where I want to do that, but now I'm taking a metal tube with wood inside of it. Why would I want to do that? I've just made it heavy, right? Why don't I just take a metal tube with the right wall thickness, right, Jason? And then I have a hollow one, and I don't have anything in the middle of it. Now I could take the metal one and put metal on it, but then I got to get the two metals apart. Now that can be done. How do you have too much? Do you know much about thermal expansion? Have you talked about that yet?
No.
In that case, what you might want to do is take an aluminum mandrel or tube and spray steel around it, and then you can take really low temperatures on aluminum. It contracts or shrinks faster than steel does. It will shrink and then it'll break away from the metal, and then now you have a metal tube that you can spray it. That's why I came up with this. This is the easiest one. Because I can take very high temperature materials, titanium, or even put ceramics onto this. And this is very friable. I can just go in there with a very soft brush and drill it through there, and it just turns into a powder, just dumps out, and voila, I'm done. Does that make sense? So, I have different choices. I want you to feel them, kind of get an idea here, but each one has its place in the building of something. So I'm going to give you an example here. So you pass this around to the other side and have it come the other way. My son and I, we're motorcycle guys. So what we did is, this is a fairing on the side of my motorcycle. And he didn't want a plastic one, he wanted a composite one. So I took some graphite composites and built one, but feel the difference in the weight of them. They both will function, but there's a tremendous difference in the weight. So now, what does that help him if he's racing his motorcycle? What does that do? If I've made his motorcycle lighter, which one's heavier? That one's plastic. The heavy one's plastic. Very good. So what's going to happen to his motorcycle now if we made a bunch of composite things and made it lighter? Faster, right? He can use the same power and go faster because we've reduced the weight of his vehicle. So pass those around. Yes?
If you wanted more motorcycle, you would do this. And if you wanted more of a set motorcycle, you would do this.
You do what? because if you do the stunts and crash a lot, you might want to have composites because they'll last a lot better than the plastic. Okay, properties. Why do they matter when building a rocket? Properties. You know what properties are?
Keep an eye on it.
Yeah, good.
Physical or chemical?
Pardon?
Physical or chemical properties?
Yeah.
Could be both, right? Yes?
The things that, the properties of something that, like a chemical or matter, is kind of something that can work, how something works. Like, that can bend the plastic with the logo.
Yes, very good. So you walk right into the application here. I have two materials that are very close to the same thickness. I'm saying close. They're not exactly the same, but they're close. This is plastic. Look how flimsy it is. I mean, it doesn't even stay straight on its own, but this is steel. See how rigid its properties, its stiffness, how much stiffer it is than the plastic? So this may have an application where stiffness is important. This one have an application where it's not important. Does that make sense? So, materials matter and their properties matter when you're designing something. Yes?
Graphite seems to be the lightest, too.
Yes, it does. The graphite's the lightest as well, right? So that's why graphite is such a good candidate for space stuff, because it can stand, it's very stable, right? When it sees very cold and very hot, the back plane on this James Webb is that. So, what I want to show you here is the James Webb Space Telescope. Sunshield project, and that's what I want you to be involved in. So this is what we're going to do. We're going to actually see the Sunshield right here. This is what Mr. Jason
How many
and I
of you, how many of you want to see my Sunshield? So most of the kids got to come to layer 3 or 4.
Okay, this is layer 5. We're actually going to be building. What we're going to do today is you're going to help me build a Sunshield like this, and we're going to set it up in the museum in this very spot, right under the Saturn V at the Davidson Center, May 14, 2016. So this is how many bags it's going to take. It's going to take about 3,000 coffee bags to do that. We've already assembled 1,300. Hopefully you're going to help me with like 30 of them today. And this is how it's going to, well, in here, this is how it's going to lay out. The small bag, which I'm showing you the sample of here,
So the kids who came to see this in my office for work, this is the pattern that we use to build the real Sunshield. So you see the different colored sections that Mr. John has here? Our Sunshield, we made of 5 different sections and put it all together. But each row here is an individual piece. So
there's 55 of them. Right?
there's 55 of these larger pieces that we talked about when you guys came to see me. And Mr. John's going to make them out of little coffee bags.
Little coffee bags. I'm going to use approximately, it looks like I'm going to use about 1,400 of these now. This was made before when I was first thinking about it. I'm going to use 1,400 of these, but then today, then what we do is, you can do this today, but we're going to use the big ones because I had to get done fast. Because I got this project. So what we do typically at the schools, we take 9 bags, like this, the coffee bags, like at work, and we tape them together to make a long piece, which would be similar to one of these long pieces here. But these aren't quite wide enough. This is only 8 inches wide here, so we have to have about 6 of them wide in order to be wide enough to fit just one piece right here. That's why it takes so many of these bags in order for us to build Sunshield. Does that make sense? Now, because they're coffee bags, they have that on it. That is going to work in a real Sunshield. But the neat thing is on the inside, it has the shiny silver stuff. And that's what caught my eye. I go, this is cool. It's shiny silver. This is like the real Sunshield stuff. Not quite as shiny, but this is what we're going to do. So, good? You got that? See how that's done together? So we're going to start. We're going to go back here. We're going to go on the table. So get these chairs out of the way.